Welcome to The Explainer. Today, we are diving into a paper that's teaching AI a brand new skill. Not just how to talk, but how to act. We're going to look at a huge shift from AI that just describes what to do to an AI that can actually execute tasks using the most powerful tool for controlling computers we have, code.
I mean, really think about that for a second. We're all used to talking to large language models, right? You ask it something, you get a text answer back. But what if you need that AI to actually do something on a computer, not just tell you how to do it? Well, that is the massive leap from a simple chatbot to a true AI agent. And as it turns out, it's been a really tough nut to crack.
So let's get right into the core problem. Researchers call it the action bottleneck. Picture this. You have an AI that is brilliant at planning the perfect vacation for you. It knows the best flights, the coolest hotels, all of it. But when it's time to actually go online and book those things, it hits a total wall. That gap right there between knowing what to do and actually doing it, that's the bottleneck.
Now, the early solutions were, kind of clumsy. They basically gave the AI a fixed menu of commands. It could say, click button X, or output a structured file to look up a price. But this was super rigid. I mean, every single possible action had to be pre-programmed. The AI couldn't mix and match tools or handle complex logic. It was like trying to write a novel using only a dozen pre-approved sentences. What was really needed was a single flexible language, a unified action space that could express pretty much any command you could dream up.
And this visual just drives home how inefficient that old way was. Here on the left, you see an agent trying to find the cheapest country to buy a smartphone. It's this painful back and forth. First, it has to look up the exchange rate for Germany. Then it waits. Then it looks up the phone price, and it waits again. Then it has to convert the tax, and wait again. It has to do this for every single country, one tiny step at a time. It's just slow and incredibly clunky.
So how do you smash through this bottleneck?
Well, the researchers behind this paper came up with a solution that is just beautifully elegant. They thought, instead of giving the agent this limited menu of actions, why don't we just let it speak the computer's native language? Why not let it act by writing and running code?
And that right there is the core idea behind something they call CodeAct. It's a framework where the agent's action isn't some simple command. No, its action is a whole block of executable Python code. And this one change completely unifies every possible digital action, from calling a web API to doing complex math, all into one flexible and incredibly powerful space.
This slide just says it all. On the left, you've got that slow, painful, step-by-step process we just saw. But on the right, with CodeAct, it's a whole different ballgame. The agent writes one single block of Python and makes a list of countries and uses a for loop to run all the lookups and calculations for every country in one shot. That is a massive leap forward in both efficiency and what these agents are capable of.
So why does this work so incredibly well? Well, it boils down to four key things. First off, the agent gets immediate feedback from a Python interpreter. It either works or it gets an error message it can use to debug itself. Second, it can tap into the entire universe of existing Python libraries for stuff like data analysis or making charts. Third, these big language models have already seen tons of code in their training data, so they're already familiar with it. And finally, code just naturally handles things like loops, variables, and if-then logic, which is exactly what you need to solve complex, multi-step problems.
Okay, so a great idea is one thing, but you've got to prove it works, right? Well, the researchers put CodeAct through its paces. They ran extensive experiments, pitting it directly against the older text and JSON methods across 17 different language models.
And the results were pretty striking. When they tested these agents on complex, multi-step tasks, the agents using CodeAct had up to a 20% higher success rate. Now, that's not just a small bump. That means for 1 out of every 5 tasks that older agents would completely fail, the CodeAct agent got it done.
And it wasn't just about being more successful, it was about being way more efficient. The CodeAct agents needed up to 30% fewer actions to solve the same problem. This goes right back to that smartphone example we saw. Instead of dozens of tiny steps, the agent can bundle all that complex logic into one powerful action and get to the answer so much faster.
Now let's see how this plays out when you use a really powerful model like GPT-4. This chart here shows the success rate for each method. And while the older text and JSON methods do okay, CodeAct is the clear winner. It's not even close. And this tells us something really important. The more capable the underlying language model is, the more it benefits from the power and flexibility of using code as its way of acting.
So, what does all this power and efficiency actually look like in the real world? Let's move past the numbers for a second and check out a task that would have been, frankly, almost impossible for the older agent frameworks to handle. So in this example, a user gives the agent a pretty complex data science task. They give it a link to a data set about cars and ask it to download the data, clean it up, prepare it, and then build a whole machine learning model to predict a car's fuel efficiency. I mean, this is a sophisticated multi-step workflow.
The CodeAct agent gets right to work. It imports the right libraries, it knows it needs pandas and scikit-learn, and it writes the code to do the job. But then, bam, it hits a value error. The code breaks. And why? Because the data isn't perfectly clean. This is a classic problem that literally every developer runs into.
But this is the amazing part. The agent doesn't just crash and give up. It reads the error message, it understands the problem, and you can see its thought process. It seems there is a data type issue. And then it writes new code to fix the problem and tries again. This is autonomous self-debugging. That's a critical skill for any programmer, and we're seeing an AI do it all on its own.
And after debugging its own code, the agent just keeps going. It even handles a follow-up request to visualize the results. It hit a common roadblock, figured it out, and completed a complex, multi-part task entirely on its own. This is a real glimpse into the future of what AI assistants could be for developers and data scientists.
So what's the big takeaway from all this? Well, this research really points to a fundamental shift in how we're going to build autonomous AI. The future isn't just about talking to our computers. It's about giving them executable instructions and then letting them get to work.
You know, the authors themselves say that this is just the beginning. That self-debugging we just saw, that's a basic form of learning. Future agents could try thousands of tasks, learning from every single error and success, and use that knowledge to get better and more reliable all on their own.
And that leaves us with a pretty fascinating final thought. When we give AI agents the ability to not just think, but to act, to experiment, to fail, and to self-correct just like a human programmer does, what new frontiers does that open up? What truly complex problems in science or engineering or anywhere else will they help us solve next?
This is for entertainment purposes only.